So here we're working out how to calculate air pressure as a function of elevation, or in general how to calculate fluid pressure as a function of vertical position. So we're going to model the fluid as a stack of blocks. So I've highlighted 3 stacks of blocks in yellow here, these 3 columns of air stretching all the way up to space, and in particular highlighted 2 of these cubes of air in green. And we'll focus on this one first, this block of air at the bottom of this column holding up this entire column. So here's the free body diagram for that bottommost block of air. We've got this is a 1 meter by 1 meter by 1 meter cube of air. We've got its own weight, the force of gravity on the cube, due to the masses of all of the air molecules in that cube. So there's that force of gravity. There is an upward normal force on the cube from the ground, and then a downward force from the entire column, this contact force here pushing down on it due to the pressure at this interface between the column and the block. That's F1 here. I'm calling it 1 because that's the pressure at an elevation of 1 meter above the ground. F1 right there. The force due to the pressure at that elevation. So in hydrostatic equilibrium, the net force on that block is 0. So here's our sum. So we can work out that that force on the block from the column above due to the air pressure pushing down on it, F1, is given by this difference here. So the normal force minus the tiny weight of that cube of air, which is the mass of the cube times little g. Let's represent the mass of the cube as the density of the air making up that cube times the volume of the cube. And now here's some approximations. We'll use simplified numbers here. We'll approximate that normal force as 10 to the 5th newtons, as we calculated earlier, 10 to the 5th newtons pushing upwards on this 1 by 1 column of air extending all the way up to space. Then the density of air will approximate as roughly 1 kilogram per cubic meter. The volume of our cube is 1 cubic meter. And then for little g, instead of 9.8, let's just approximate it as 10 newtons per kilogram to make the numbers simple here. So meters cubed cancels meters, kilograms cancels kilograms. And what we'll find is that the force pushing downwards on this green cube from above is 100,000 newtons minus 10 newtons, leaving behind 99,990 newtons. That's this force pushing down, which means the pressure exerted on this green cube from above, that is the pressure at a elevation of 1 meter above the ground, is given by that force, this force right here, divided by the cross-sectional area over which it's being exerted. So the 1 square meter area of the top of that green cube. So that many newtons of force acting over 1 square meter gives us 99,990 newtons per square meter. And let's convert that to atmospheres. We know there's about 10 to the 5th newtons per square meter in an atmosphere. So newtons per square meter cancels newtons per square meter. And the air pressure at 1 meter above the ground is therefore 0.9999 atmospheres. So a little bit less here than at the ground where it is 1 atmosphere, just a little bit less than 1. Okay, let's next look at this green cube, the one just above the bottommost one. Let's go a little higher up. So now the FBD for this 1 cubic meter of air right here on top of the bottommost cube. So the net force on it will also be 0. It has its own weight here. And then F1, we just calculated this, this many newtons right there. If that's the force that this column was exerting on the bottommost cube, then by Newton's third law, that bottommost cube is exerting that same size force upwards on the base of the column. So the force from the bottommost block onto this green block, that upward force F1, is that same 99,990 newtons. And then there will be this force from the column overhead pushing down on the green cube. We'll call that F2 because it's the force due to the pressure at 2 meters above the ground. Okay, let's compute that force, the force due to the pressure at 2 meters above the ground, the downward force from this column onto the green cube. All right, so that'll be F1 minus the weight of this cube here. So that 99,990 newtons minus the weight of this cube. And since this cube is the same volume as the previous cube, we know its weight is the same as the weight of the previous cube, being 10 newtons. So subtract another 10, and we get F2 here, pushes down with 99,980 newtons. Divide that by 1 square meter for the cross-sectional area of the top of this green cube, and convert that to atmospheres, and we get 0.9998 atmospheres at 2 meters above the ground, just a bit less than at 1 meter above the ground, which was just a bit less than at the ground itself. Okay, so compare these values. We see the air pressure dropping very slightly as we go up to higher elevations. That pressure difference between the top and bottom of a fluid element in hydrostatic equilibrium, the pressure difference we could represent as the difference between the force per unit area at the bottom pushing upwards and the force per unit area at the top pushing down. We know the pressure below is always going to be greater than the pressure above, so the pressure below minus the pressure above will give a positive number. And we see that the difference between those two forces, F1 and F2, is the weight of that cube. So the difference between the pressure below and the pressure above is equal to the weight of the cube, the weight of the fluid element, divided by the cross-sectional area. So the weight per unit cross-sectional area. That's the pressure difference. That is, the difference in pressure from above and below has to be just enough to balance the weight of the cube, that force of gravity right there. So let's rearrange this a bit. The mass of the cube we can represent as the density of the air in the cube times the volume of the cube. And then if this is our green cube right here, whose volume is equal to its cross-sectional area times its height, A times H, then this quantity, V over A, the volume divided by the cross-sectional area, is equal to the height of the cube. So replace V over A with the height H and get this formula. The difference in pressure above and below some fluid element is given by the density of the fluid times little g times the height of the fluid element. And this is our first important equation for our study of fluid mechanics, rho GH for pressure difference. For air, if the density of air is about 1 kilogram per cubic meter and little g is about 10 on Earth, newtons per kilogram, and we look at a height of 1 meter, we see that the change in pressure in air for each meter is about then 0.0001 atmospheres. That is, we're dropping by 0.001 atmospheres, 0.001 atmospheres every meter. So our picture of this sort of pressure structure of the atmosphere looks like this: 1 atm at the ground, and then we drop by 0.0001, that is 1/10,000th of an atmosphere every meter above the ground. So the air pressure does decrease as we go up, but very slightly. So slightly that we're not going to notice it until we start going up hundreds or thousands of meters. You go up to the high elevation mountain ranges and we'll see air pressure different noticeably than near sea level. But you'll never notice a difference in air pressure between the first floor and the second floor of your house. So in all of our thought experiments that follow, we're going to ignore any changes in air pressure unless we're looking at altitudes of hundreds or thousands of meters. Okay, so pressure has entered the picture here. We'll have lots of calculations coming up, and as it turns out, there is just a proliferation of different units that are used for measuring pressure by different industries, by different in different professions, different standards. So the SI unit that we'll stick with for our calculations, the Newton per square meter, it does have another name. It's called the Pascal, abbreviated capital P, little a. So 1 Pascal is by definition the same thing as a Newton per square meter. So for short, we can say pascals instead of newtons per meter squared. We've also introduced atmospheres, and when measuring barometric pressure, we'll use millimeters of mercury or inches of mercury. We'll discuss those later. And in the US, engineering and industry, we use pounds per square inch, or PSI. So what you should know, and there's even more than these, there are so many pressure units. What you should know, or what is helpful to know, is what 1 atmosphere is equivalent to in each of these different units. So we've already shown that 1 atmosphere is approximately 101,300 newtons per square meter, or pascals, 101,300 pascals, or so that's in blue, that's our SI unit, or 101.3 kilopascals, or here's another unit, 1.013 bars. 1 atmosphere is very nearly the same as 1 bar, but not quite. It's 1.013 bars of pressure. 1 atmosphere is also equivalent to about 30 inches, 29.9 inches of mercury, or 760 millimeters of mercury, also known as 760 torr. This is the unit used when measuring air pressure, barometric pressure. Or 1 atmosphere is 14.7 pounds per square inch, 14.7 psi. See, the pressure on your body in the room you're in right now is about 15 pounds of pressure pushing on every square inch of your body. For comparison, your car tires probably require inflation to about 32 to 35 psi. So that if 1 atmosphere is about 15, that means the pressure in your car tires is about twice that, or about 2 atmospheres. So your car tires are at higher pressure than the surrounding air, which is why they explode when the inner tube is punctured and the air bursts out under pressure. Truck tires, for comparison, are going to have a pressure in them that could be up to 70 psi or up to 5 atmospheres in a truck tire, which is why when truck tires blow out, they really explode, and you'll see that debris left by shredded truck tires along a highway.